In section 3.2, we're going to talk about derivative. But before we do that, let's quickly review what we've done so far in this chapter. In section 3.1, we talked about two special applications. The first one was called the slope of the tangent line. And we came up with this formula for the slope of the tangent line. We had the limit as h goes to 0. We had f of x plus h minus f of x divided by h. And the second application we took a look at was instantaneous velocity. And the formula we came up with there was v is equal to the limit delta t goes to 0, and we had s of t plus delta t minus s of t over delta t. In the first case, the function that was given to us was y is equal to f of x, and out here we were given some position function s of t. Okay, both of these formulas are exactly the same, they're just using different notation. So this formula that we came up with in these two completely different applications, one application is from geometry and the other one is from physics. They both share something in common, which is the formula. So this formula must be special. And in this section, we're going to call this formula the derivative. Okay, so let's talk about that. So here's the definition. The derivative of a function y is equal to f of x is a, and I'm going to capitalize this because this is something important, is a new function. So we end up with another function when we take the derivative, is a new function f prime of x, okay, defined by f prime of x is equal to the limit as h goes to 0. We have f of x plus h minus f of x divided by h, provided the limit exists and is finite. That means it cannot be infinite. Okay, so this formula that we came up with in the previous section, I'm just using the f notation instead of the s and t, is called the derivative. Okay, and this formula the derivative exists if this limit on the right hand side exists. Okay, there are lots of notes that I need to write down regarding this, so let's start with them first. Okay, if the derivative exists, at some x is equal to a, okay, then we say the function is differentiable. We say that the function is differentiable at a. Okay. 2. Okay. There's some variations of that formula. Sometimes you'll see formulas, variations of the formula. To me, this is a more general formula. It works for any x, but sometimes you'll see formulas like this. There are two options. One, they will replace x with a, so we get f prime of a is equal to the limit as h goes to 0. We have f of a plus h minus f of a divided by h. So this gives us the derivative at x is equal to a. So that's one variation where you have a specific point. Another variation is in the previous formula, if we replace h with x minus a in the previous formula, the general formula, that means we have out here we have, oops, sorry about that, goof up. Yeah, that's fine. Okay, so in this formula up here that I have here, okay, I'm going to replace, actually, let me do this better. Let's do this. We're going to go let x is equal to a plus h in this formula up here. Okay, so let's see what happens. Well, if h goes to 0, okay, if h goes to 0, then where does x go? If this becomes 0, then x will go to a. Then x approaches a. So that's the formula we get. So I get f prime of a is equal to the limit. Instead of h going to 0, we're going to say x goes to a divided, as x goes to a, f of a plus h. But what is a plus h? We called a plus h what? X. So we get f of x minus f of a. What is h then? Well, if you solve this for h, what do we get? We get x is equal to a plus 8. So h is equal to what? X minus a. You move the a to the other side. So we get x minus a. So here's another formula that gives us the derivative at a. Okay, so here's another formula that gives us derivative at a. So you have two variations of the formula, okay? And they're basically the same formula that we have here, except we're changing x to an a specific point. And then the second formula is we're just making some type of a substitution to get a different formula. This formula is mainly used a lot in proving theorems. So it's used in proofs, okay, not so much in calculations. When we want to find the derivative, we usually tend to use this one. You can use that one too, the one I gave you here, or this one, doesn't matter, whichever one, but usually it's the top one that we use, okay? All right. 3. In this class, actually, let me write down. So derivative, just so you know, derivative is the instantaneous rate of change of one variable with respect to another. Okay, so I'll come back to that if you didn't copy. You can always pause the video and copy and then continue. And you also don't have to watch the entire video continuously. You can watch the first half an hour and then the next half hour. You can always pause these videos. So you can see out here, y is just f of x. So this is all y. You can think of it as y. Okay, so the derivative is just the rate of change of one variable, which in this case is y, with respect to x. Okay, that's what it is. But it is the instantaneous rate of change. That's what makes it special. Okay. In this class, we will always think of the derivative as the slope of the tangent line. Depending upon what type of application you're doing, the derivative might mean different thing. For example, if you're in physics, usually the derivative would be velocity. Okay, if you're in business, derivative could be the marginal cost or the marginal profit. It just depends upon what you're working with. In all of those cases, basically the derivative is the instantaneous rate of change of one variable with respect to another. When we talk about the slope of the tangent line, we are talking about the instantaneous rate of change of y with respect to x is what we are talking about, because slope is what? Rise over the run is what we're doing. Okay, except we're doing the instantaneous rate of change. Okay, 5, we have notations. There are a couple different notations depending upon which class you're in. um, if you're doing an upper division math class, usually we would use Leibniz notation, which would be dy over dx. Normally, a change in mathematics is denoted by delta, so the rate of slope would be what? Delta y, change in y over change in x, which would be rise over the run. But because derivative is the instantaneous rate of change, instead of using deltas, we use d's. Okay, so that means it's instantaneous rate of change. Okay. Leibniz was one of the mathematicians who's credited with inventing calculus along with Newton. He used this notation for derivative dy over dx. He was very explicit. He was talking about change in y, instantaneous change in y over change in x. Newton, who came from the physics background, used this notation y with a dot, or we could have f of x with a dot. So he used the dot notation. Lagrange, who's another French mathematician, he used the prime notation, which is what we will use the most, y prime or f prime of x. So that is a notation we will use the most, is Lagrange's notation, but we will never use Newton's notation in class. We will use Leibniz every once in a while, but Lagrange is the one I will usually use. It's easier to write. Okay. 6. So let me label this so you don't have to keep scrolling. Let's call this 1, equation 1, or formula 1. Okay. So we won't be using formula 1 anymore. We just used that in the last section. So from this section forward, we'll use shortcuts to find derivatives. Okay. So we will use shortcuts. We'll talk about what they are. Shortcuts to find derivatives from this point forward. Okay. But always remember, anytime you're finding the derivative for the very first time of this new function, we always use the formal definition. So use the formal definition, and by that I mean definition 1 that I labeled up above. Use formal definition to find the derivative of a new function for the very first time. Okay, like for example, later on in a couple sections from now, we will find the derivative of sine x. We don't know what that is right now. So when we do that for the very first time, we will use the formal definition. But other than that, once we know what that is, you'll find out the derivative of sine x is cosine x. Once we know that, once we do that with the formal definition, going forward, we will always assume that the derivative of sine x is cosine x. So we don't have to do it formally every single time, just once for the very first time. Okay, so those are some notes on derivatives. Okay, we can also take higher derivatives, just so you know. Okay, we can take higher derivatives. Okay, that is okay. So let's say that we have this. We did this in the last section. S of t was the position of a particle, position of an object. Let's call it an object at time t. Okay, and we learned that If we use this formula, we ended up with something called instantaneous velocity. And this formula is basically just the derivative except with different notation. Is that okay? Instead of f and x, we have s and t, and instead of h, we have delta t. So when I take the derivative of position, we end up with velocity. So we get velocity of the object at time t. Okay, and we can denote it by v of t. If I take the derivative of velocity, how fast velocity is changing, this tells us how fast the position is changing or displacement is changing. Position is the same as displacement. Okay, how fast position is changing with respect to time, and it gives us the instantaneous rate of change. If I do the same thing, if I take the derivative of velocity, I get something called acceleration, which tells us how fast velocity is changing. Okay, so we know velocity is s prime, so this is the same as what? S of t, I'm sorry. This is the same as s prime of t, and this prime here I'm going to put outside prime because velocity is s prime. So this gives us s double prime of t. So another formula for acceleration is s double prime of t. So this is acceleration, okay, of the object at time t. So we can take higher derivatives. Does that make sense? Okay. It just gives you the rate of change of the previous variable with respect to whatever variable you're working with. In this case, we are working with time. Okay. All right. So in general, the notation for higher derivatives, okay, general notation. So I wanted to show you that we can take higher derivatives and they have some meanings, like you saw with velocity and acceleration. Okay. Out here, acceleration is the second derivative of position, but it is the first derivative of velocity because it measures the change in velocity. That's what acceleration measures. Velocity measures the change in distance, okay, over time. So the general notation is this. If you want to take the nth, actually, let's do the first couple. So I'll only do Leibniz and Lagrange's notation. So if you take the first derivative, that means if we're just taking the first derivative, we have y prime of x, or you can write it as dy over dx, or you could have f prime of x or df over dx, doesn't matter. Second derivative would be y double prime of x, or we have d squared y over dx squared. Okay, now you have to remember what we are doing. We are taking the derivative of a derivative here when we do the second derivative. So this is basically d, the derivative of a derivative, because we're taking the second derivative. So we take the first derivative and then take the derivative of that again, and that's why we get d squared. We have two d's there, and then dx is also doubled up, but that whole thing is doubled up now, and that's how this comes about. Okay, anything above the second derivative, we use a different notation. For third derivative and higher, we write it this way with parentheses 3x. Okay, or if it's the seventh derivative, we would write it this way, and so on. So in general, we would write it this way: y to the nth derivative, where n could be the 3, could be 4, 5, 7, or whatever, or we can write dn y over dx to the n. So these are higher derivatives. So this is the notation we will use. okay, for higher derivatives. For the first two derivatives, we use the prime notation, but anything above that, we use these parentheses with an n. That's not an exponent, that just tells you you're taking the nth derivative. All right. So now that we know what a derivative is, it's an instantaneous rate of change of one variable with respect to another. Let's go ahead and take a look at some examples of derivatives. Okay. Okay. Let's start with the easiest one here. Let's say if I give you this function y is equal to c, where c is some constant. What does a graph look like? So if this is x, this is y. If I draw a horizontal line going through c, so this would be y is equal to c, the graph of that. Now on this line, if I pick any point and draw a tangent, so let's say if I pick this point and draw a tangent, the tangent will also be horizontal. And since we said earlier, derivative is just the slope of the tangent line, okay? So if it's the slope of the tangent line in this class, that's the main way we're going to think about the derivative in this class. What is the slope of the yellow line here, which is the tangent line? So t is the yellow, tangent line. If you look at it, it's flat, so the slope is going to be 0. So from here, we can extrapolate that the derivative of a constant is 0, 2. If I have y is equal to some mx, so that line looks like this. M is some number, so it would look something like this. So this is the graph of y is equal to mx. Okay. Once again, if I pick any point on this line, let's say this point, and draw a tangent line there, that tangent line will be the same as the line that we have here. What is the slope of this line? Well, slope is always the coefficient of x once you isolate y. Y is already isolated, so slope here is just m. Okay. Out here, the slope, just so you know, is 0 because it's a horizontal line. That's why the derivative was 0. Out here, the slope is m. And since the tangent line and the line that was given to us are the same, the derivative of this function is just going to be m. So if you take derivative of mx where x has power 1, you're just going to get a diagonal line. So the derivative of that is always going to be 1. For 3, if I have y is equal to x squared. Now this one I'm going to do it using the formal definition. Anytime I say the word formal definition, we are talking about this definition, okay? So please remember that. That will be referred to as the formal definition of derivatives. What did I say? Anytime you do the derivative for the very first time, we always want to use the formal definition. Is that okay? That's what we said that. Other than that, we will use shortcuts. So let's do that. So we get y prime, my derivative is going to be the limit as h goes to 0. We get x plus h squared minus x squared divided by h. Out here, this is my function f of x that we are working with. So we get f of x plus h. F of x plus h would be just x plus h squared in that. If you look at this limit, it is 0 over 0. So we need to do some algebra. So it's no longer 0 over 0. So in this case, I'm just going to expand it. So I get x squared plus 2xh plus h squared minus x squared over h. I just FOIL that, and the x squares will cancel. The two terms that are left have an h in it, so we can pull it out. So we get 2x plus h divided by h. The h's will cancel. Now it's no longer 0 over 0, so we can plug in h is 0. When I plug in h is 0, this will become 0. So I'm just left with 2x. Okay, so the derivative of x squared is 2x. So if you do the same thing, it's 4. If I give you y is equal to x cubed, so this is going to be my function now. And if I went through the same exact steps, so I did y prime is the limit as h goes to 0. I have x plus h cubed minus x cubed divided by h. All I did is replace I'm just using that formal definition. Again, I'm replacing f of x plus h, which happens to be x plus h cubed since f of x is x cubed. And now it is 0 over 0. So we'll expand it. So we'll FOIL that again. Okay. So we get x cubed plus 3x squared h plus 3x 8 squared plus h cubed minus x cubed divided by h. So I FOILed this. I took x plus h and multiplied it by itself 3 times. Okay. Then anything in this will cancel. Then we have an h common in all the other terms. So we get 3x squared plus 3xh plus 8 squared divided by h. Cancel the h's. Now it's no longer 0 over 0. So we're going to replace every h with 0. There's an h here that becomes 0. This becomes 0. So I'm left with just 3x squared. And you can keep doing this. But let's see if we can come up with a nice formula. So we learned this. We learned that so far we've learned this. Y is equal to constant. Give the let's write it in a table form, might be nicer. Okay. Here is y, my function. Here's my derivative. If I have a constant function, the derivative is 0. If I have mx, or actually let's just call it x, what was the derivative? If you look out, if I had this function, what was the derivative here? Well, in our case, I said y is equal to x, so m is 1. My derivative was just m. M is 1 in this case, so the derivative would be 1. If I have x squared, we found the derivative was 2x. And if I have x cubed, we found the derivative was 3x squared. And if you continue this, you can come up with a nice formula for x to the n. If you notice in all of these cases, what's happening? Even in this case, okay, we have 1. And even in this case too, you can think of it as x to the 0, but let's do that. The 1 comes in the front and you decrease that by 1. So I get 1 in the front and you decrease that by 1. So you get 1 minus 1. So you end up with 1 times x to the 0. Anything to the 0 is 1, so we get 1. Out here, the 2 comes in the front, so we get 2. And you decrease that by 1, so we get 2 minus 1. So we get 2x to the 1, which is what we have here. Out here, the 3 comes in the front and you decrease the exponent by 1, so we get 3x squared. So in general, if you have an n here, okay, the n will come in the front and you decrease that exponent. So this is an extremely important derivative that you should know. So let me write it up on its own. So the derivative, I'll use Leibniz notation, of x to the n is equal to n comes in the front, x times n minus 1. Okay. So that is the derivative, and we call this a power function. So that is the derivative of a power function. So derivative of a power function is you bring the exponent in the front and then decrease that exponent by 1. Right. So now we know how to take derivatives of some function. So now going forward, we don't have to use these formal definitions anytime we are given a power function. We just do what we did here, bring the n in the front and decrease that. And I'll give you some examples of that in a second. But before we do that, let's take a look at some properties of derivatives. For now, there's many other properties that we'll come across throughout this chapter, but for now, we'll start with 2. Let f of x and g of x be 2 differentiable functions. All that means is we can take their derivatives, differentiable functions, and c a constant. So c is just some constant. Right? So now we have 2 properties of derivatives that we're going to work with now. Okay. So the first property is this. If I take the derivative, I'm going to use Leibniz notation, of some constant times my function f of x. Just like with limits, I can pull that constant in front of the derivative. So I can write it this way. C times the derivative of f of x. Just like we did with limits, we can take the constant out, so we can do that. The second property is when you take the derivative of a sum, if I have f of x plus g of x, then I can, just like with limits, I can distribute the limits. I can do the same thing. I can distribute the derivative, so you can get the derivative of the first plus the derivative of the second. So we can go ahead and distribute that derivative. Okay. So this is referred to as term by term differentiation. So we call this term by term differentiation. Okay. And it'll be used a lot. You'll see that. Okay. Now that we know these two properties and we know some basic derivatives here, let's put them together and do some examples. So let's say if they give us, I'll do two quick examples. Let's say they give us f of x is equal to 4x cubed minus 5x to the minus 3. I'm sorry, let's use a different number. Minus 7 plus 6x raised to 2/3 plus 7 square root of x. Okay, and let's throw in one more, minus 1 over x squared. So let's say I'm given this and they want us to find f prime of x, which means they want us to find the derivative of this function. Now, we could try to use the formal definition, which will get absolutely cruel. We can see all these goofy terms we have. So this is where the shortcut comes handy. Now, to use the shortcut, the only true derivative we know, really, when you think about it, are two. We know the derivative of a constant is always 0, and we know that the derivative of a power function, which is also right here, because these are all power functions in essence. So the only two we know are these two. Okay, this is the same as this. Okay. So we just want to use those two. Let me throw in a constant 2 out here, plus 10. Right. So let's use these two properties that we have. So the first thing is when you take the derivative, we can do term by term and we can pull constants out. So out here I can take that constant out and then I just take the derivative of the first. I'll write it as a prime. Okay. Out here I use Leibniz notation. I could have easily written this way using Lagrange's notation, the prime notation. So I get f prime of x, derivative of the first, plus the derivative of the second, same thing. Minus, once again, I can take the constant out, x to the minus 7 prime. I want to take the derivative of that, plus 6 x to the 2/3 prime, plus 7 x to the 1/2 prime, because square root of x is x to the 1/2, minus x to the negative 2 prime. So 1 over x squared, we want to write it as a power function. So that will be x to the negative 2. Okay. Now the and we also have the 10, I forgot, 10 prime. So all we've done is use this property and this property, which tells us that I can take derivative term by term, and I can also pull constants outside my derivative. So I did that. Now let's do that. Since this is a power function, what will happen? The 3 will come in the front and the exponent will decrease by 1. Since this is a power function, the negative 7 will come in the front and the exponent will decrease by 1. So you get negative 8. Plus, out here we get 6 times the exponent will come in the front and you decrease that by 1. So 2/3 minus 1 is negative 1/3. Plus, we get 7. The exponent will come in the front and you decrease half by 1. So you get minus 1/2. Minus the exponent will come in the front and you decrease that by 1. You get this, and the derivative of a constant, if you recall, was 0. So for all of these we use the power function for the first 1, 2, 3, 5 terms, and the last one we use the fact that the derivative of a constant is always 0. And now we can just clean it up. So we get f prime of x, we get 4 times 3 is 12x squared. Negative 5 times negative 7 is plus 35x to the 8 plus 3 and the 6 will become a 2. 2 times 2 is 4. X to the 1/3. I'm moving the negative exponents down again. Plus 7 to x to the 1/2. Again, moving that down. This negative and negative will become a positive, so I get 2 over x cubed. And the next thing you would do is find the common denominator and add them up. But right now, I don't want to focus on that. I just want to focus on taking the derivative. Okay, and there's your derivative. So you just do it term by term. Okay, let's take a look at another example. Let's say they ask us find all points on the curve. Okay, now they're going to give us a goofy curve or something like that, and they want us to find all points on this curve. F of x is equal to, okay, 3x squared minus 2x minus 4, okay, at which the tangent is horizontal. Okay, if you recall, we talked about horizontal tangents in our class. What is one special feature of horizontal tangents? What that basically means is the slope of the tangent line is 0. Okay, and we know from earlier today, slope of the tangent line for us will mean just the derivative. So that means the derivative is 0. So that's what we mean. If you were to graph this function, I don't know what the graph looks like, but it's going to be some type of a parabola, so it'll be like this. So you can see there's clearly only one point where the tangent is going to be horizontal. So this is my tangent line. So we want to find this point. That is the question, right? So I know that the slope of the tangent line is my derivative, and I want to take my derivative and set it equal to 0. So let's find the derivative first using the two properties that we have. So I'll go y prime. This is the same thing as y, right? So I'll go y prime. This time I'm going to do it on the fly. Out here, I wrote all the steps out for you just to show you how the two properties that I gave you worked. But now I'll just do them on the fly. This is a power function. How do you take the derivative of the power function? You bring the exponent in the front. So 3 times 2 is 6. And you decrease that by 1. So you get x to the 1. Derivative of this, the exponent is 1 here. So you bring the exponent in the front. So you get negative 2. And then you decrease the exponent by 1. So you get x to the 0. Anything to the 0 is always 1 in algebra, correct? So we get that. This is a constant. So derivative of a constant is always 0. So we get this. So there's my derivative. Now all we have to do is take our derivative and set it equal to 0. And then we solve for x. So we get x is equal to 1/3. You move the 2 over and divide by 6. So that tells us that the x coordinate of this point is 1/3. And to find the y coordinate, you take this x and plug it into this original function. So to find y, we will get f of 1/3, which is going to be 3 times 1/3 squared minus 2 times 1/3 minus 4. So we get 1/3 squared is 1/9 times 3 is 1/3. Okay, minus 2 over 3 minus and 4. And then we just need to find the common denominator here. So we get y is equal to 1 minus 2 minus 12 divided by 3. So we end up with 14 minus 1 is negative 13 over 3. So that is the y value. So this point here is negative 13 and 3. So my graph is completely wrong. The graph should be below here somewhere. Okay, x is positive 1/3 and y is negative, so that should be below. So my point is 1/3 and negative 13 over 3. In the last section, we found the derivative of this using the formal definition, using the difference quotient formula. But now that we know shortcuts, we can just use shortcuts. So we'll speed everything up, okay? All right, let's take a look at another example. Okay. This time what they've done is they've given us a function. So they've given us y is equal to 9 cube root of x squared, and they want us to find, okay, they want us to find the third derivative. So they want us to find y raised to 3 of x, or d cubed y dx cubed, or if you want to write it in prime notation, which you can put triple prime. So you want to find three derivatives. So you have to do it successively. You have to find the first derivative, then the second, then the third. So let's do that. So the first thing I'm going to do is rewrite this as a power function. Okay, so this is 9x raised to 2/3 because of the 3 there. So now that it's a power function, let's take the first derivative. You bring the exponent in the front. So we have 9 times 2/3. The 3 goes into 9 3 times. So 3 times 2 is 6. So we get 6x raised to. You have 2/3 minus 1. You want to decrease the exponent by 1. So the common denominator is 3. So we get 2 minus that. So you get negative 1/3. Okay. That's the first derivative. You want to take the second derivative now. You bring the negative 1/3 in the front, so that will become a negative 2. X raised to, you decrease that by 1, so you get negative 4/3. Let's take one more derivative. You bring that in the front, so you get 8/3. We get x raised to negative 7/3. So my third derivative, you can write it as a prime if you want triple prime, or you can use parentheses. It's 8 over 3 x raised to 7/3. Make sure you make your negative exponents positive. Okay, and you can do that with other derivatives, other functions too. All right. So we took a look at a lot of different types of examples of derivatives using shortcuts. Okay. Let's do one more. Okay. Let's say that if they gave us this y is equal to x cubed minus 2x squared. Actually, let's do 6x squared. And they want us to find the domain of the derivative. Okay. And they also want, so that's one thing. Two, they want us to find the equation of the tangent line at x is equal to minus 1. Is that okay? So those are the things they've asked us to find. So let's find the domain. Now to find the domain of the derivative, we first have to find the derivative. So let's do that. So this is the question 1. So these are power functions. So you bring the exponent in the front, decrease that by 1. Bring the exponent in the front, decrease that by 1, x. Okay? So that's my domain. To find the domain, we look for division by 0 or square root of negative numbers. We have neither here. So my domain here for this derivative is going to be all real numbers because there's no division by 0 or there's no x's inside an even root to worry about. Okay. The second thing they've asked us to find the equation of the tangent line. Anytime they want us to find equation of any line, we should always look for a point and the slope, correct? Well, since it's a tangent line, what do we know? We know that the slope of the tangent line is just the derivative. We know that. So let's find the slope, but we want to find the slope where? When x is negative 1. So to find the slope of the tangent line, we know it's just the derivative, but we want to find it at x is equal to negative 1. This vertical bar basically means evaluated when x is negative 1. Well, here's my derivative. So we get 3x squared minus 12x evaluated at x is equal to minus 1. Replace x with minus 1, so you get negative 1 squared is 1, so we get 3. 12 times negative 1 is negative 12 times negative 1 is positive 12. So my slope here is what then? 15. So the slope of the tangent line is 15. Now, to find the equation of the tangent line, we also need a point. We know we have the slope now, we're done. Okay. To find the point, we know the x value, but we don't know the y value. But the y value is given to us. Isn't that the y value? Replace that negative 1. So we know that y is equal to x cubed minus 6x squared. So you replace x with minus 1. So you get minus 1 cubed minus 6 times negative 1 squared. So we get negative 1 minus 6 times 1. Negative 1 squared is 1. So we get negative 7. So my point from here is x is minus 1 and y is negative 7. My slope is this. I can find the equation of the line using the point slope form. So I get y is equal to m times x minus x1 plus y1. So this is my x1, y1, and this is my slope. Instead of calling it mt, I'm just calling it m, or you can put a t out here if you'd like. Okay, so we get 15 times x minus of minus 1 minus 7. So we distribute the 15, so we get 15x plus 15 minus 7. Remember, these two negatives will become a positive. So we end up with 15x plus 8, and that is the equation of the tangent line. So you can see everything got speeded up because we use these shortcuts to find the derivatives very quickly. Without, oops, not there. That was my wrong, bad. We use shortcuts to find the derivatives very quickly without having to use the difference quotient formula. Okay, all right. So that's how we do all the same problems that we did in the last section now can be speeded up by using shortcuts. And going forward, we always want to use shortcuts, okay? All right, the next thing we're going to do is talk about where the function is not differentiable, okay? We talked about derivatives, okay? So there's two more things to talk about, and we'll do that. When is a function not differentiable? Differentiable at some x is equal to a at some point, okay? Well, that would happen two ways, okay? Actually, it can happen four different ways, but the two ways I'm talking about is where this limit does not exist. If this limit, remember, for the derivative, for the function to have a derivative, this limit has to exist and it has to be finite, has to be a number, cannot be infinite. Okay. If this limit does not exist, then this derivative does not exist. So the function is not differentiable at that a. You know, if you replace all the x's with a, then the function is not differentiable there. Or if you recall, when we did slope of tangent lines, what did we do? We picked a point here and we drew a secant line, correct? And then we kept doing it. And eventually the secant line became the tangent line. We let h go to 0, you know. And we did that from the right, but we can also do the same thing from the left. We can draw a secant line here and then keep going till it becomes a tangent line. So we can also come from the left. Because technically this limit formula means you're coming from both sides, you know. H is going to 0 from both sides. Okay. All right. So another way the function is not differentiable is if the two limits from both sides are not the same, and that would mean that the limit does not exist. Okay. All right. So now we're going to talk about when a is a function not differentiable at some point. Okay. There's four ways a function won't be differentiable. Okay. Basically, that'll happen so the first way that could happen is when you have something like this. When I have a function like this, let's say this is a, okay, and I have a hole there. It's going like this. Let me draw with a different color. And here's my function here. This is included. So how did we figure out the slope of the tangent line? If I wanted to find the slope of the tangent line at this a, what did we do in the last section? We picked a point close to it and drew a secant line. And then we moved this point closer, closer, closer as h goes to 0. You know, we did that. So if you come from the left, you'll notice that the slope of the tangent line is going to be the same as this line, right? If I take a point and draw a secant line, won't that be the same as the blue line? And since this line is horizontal, the slope of this line would be what? 0. So if you come from the left, the slope of the tangent line is 0 at this point. If you come from the right, you do the same thing. We pick a point on the right and draw a secant line. And then we bring that point closer and closer. And if you notice what's happening, let's say the slope is not zero though, but the slope is some positive number because the line's increasing. But what's happening to the slope as this point gets closer and closer, okay, this secant line slope is getting bigger and bigger. You can see the slope's getting bigger and bigger. Eventually the line's going to be vertical, and then the slope is going to be what from that side? It's going to be infinite because the slope of vertical line is infinite. So the slope from the left is zero, the slope from the right is infinite. That's why this function is not differentiable at that point x is equal to a, because the two slopes are not the same. To be differentiable, the limit has to exist, and if the limit exists, the two slopes have to be the same from both sides. And the reason why this happened in this case is because f of x is not continuous at x is equal to a. So the reason why, if the function is not continuous, you obviously cannot find the derivative there. Okay, so that's what that means, at x is equal to a. Another way this could happen is when you have a function like this. So let's just pretend if I come from the left, from the right, I want to find the derivative here at a. I pick a point and draw a secant line, then I bring that point closer, closer. Eventually that secant line will become a tangent line, which will be the same as that line. So let's pretend that this line is exactly diagonal. If it's exactly diagonal, the slope's going to be 1. If I do the same thing from the left, I pick a point and draw a secant line, bring that point closer, closer. That secant line will eventually become the tangent line, which happens to be the same line that we have. And since these two lines are exactly the same, except one's going up and the other one's going down, the slope of this line is going to be -1. So the two slopes are not the same. So that's why it's not differentiable at a. I don't know why I write down again and again. But this time it's not differentiable because we have a sharp corner. Because f of x has a sharp corner at x is equal to a. Anytime you have a sharp corner in your graph, the function is not going to be differentiable at that point. Okay? Next way that could happen is when you have something like this. Okay, so let's say this is a. So if I come from the left, what is going to happen? I pick a point here and draw secant line and then keep sliding it down and down, and eventually that secant line will become vertical. Do you guys see that? But this time when you're going this way, what's happening to the secant line is to the slope? It's getting bigger and bigger, but it's getting bigger in the negative sense because all the lines are going down. So out here the slope is going to be infinite, but it's going to be negative infinite because it's going down. Now if I come from the right, if I pick a point and draw a secant line and keep sliding it down, I'll still get another vertical line here. Okay, so my slope is also going to be infinite, except this time it's going to be still negative infinite because it's still going, the lines are going down, the tangent lines or the slope of the secant lines are going down, so the slopes will be negative, except the slopes getting bigger and bigger. Okay, and when I say bigger, I'm saying bigger in magnitude, not in sign, but bigger in magnitude. Okay, since the two slopes are the same, we get something called an we'll end up with something called a vertical tangent. We get a vertical tangent whenever we have infinite slopes. Okay, we get vertical tangent whenever the slope is infinite. Okay, and infinite. Now there's a special case of vertical tangent. In this case, the two slopes were the same. Okay, but the special case of a vertical tangent is where the two slopes are not the same, but they're still infinite. So you could have something like this. Okay, so if you look at it, if I pick a point and draw a tangent, I want to draw a tangent at A. Remember, I want to find the derivative at A. So I draw a secant line, then I make that secant line get closer and closer. Eventually, that secant line is going to become the tangent line and it's going to become vertical. So my slope out here, if I go this way, my slope is increasing in magnitude, but in sign it's going to be negative because the lines are going down. So coming from the left, my slope is negative infinite. If I do the same thing from the right, if I draw a tangent here, a secant line, sorry, the slope is positive, and if I keep getting closer, move the point over, the slope's positive, positive, but eventually it's going to get vertical again. So this time it's going to be positive infinite. As soon as a tangent line gets vertical, the slope's positive infinite. Let me draw those two pictures again nicely so you guys can see. Out here, here's my A, so here's my vertical tangent. Same thing over here. I have something like this, and this is my A, and here's my vertical tangent. That's why the slope's infinite. The nice thing about this case is this is still a vertical tangent, but this is a special case. Why? Because in this case, the slopes from both sides are not the same. One is negative and one is positive. Whenever that happens, this vertical tangent is called a cusp. So a cusp is just a special case of a vertical tangent where the two infinites are not the same. Okay, if the two infinites are the same, then we just call it a vertical tangent and leave it like that. But if the two infinites are not the same, then we call that vertical tangent a cusp. Okay, all right, so let's take a look at an example of that. Let's say if I give you this, f of x is equal to, okay, 7x to the 4/3, and I ask you determine if this has a vertical tangent. Determine if f of x has a vertical tangent at x is equal to 0, and is that vertical tangent a cusp? Because to be a cusp, it first has to be a vertical tangent. So let's see. Now, to find that, how do I know that? How did we find the vertical tangent? We check the derivatives from both sides, right? And to see if it was 0. So let's do that. Let's first find the derivative of this. So let's find the derivative of this. You bring the 4/3, it's a power function, bring the 4/3 in the front, so we get 28 over 3, 4 times 4/3, the 7 times 4/3, and decrease that by 1, so we get 3rd. Now, for the derivative to be infinite, you have to have division by 0, right? Because when we have number over 0, we get infinite. Well, out here, will we ever get division by 0? Okay, x is in the numerator, so will we ever become 0? No. So when x is 0, this is never going to be infinite. So this is not infinite, so there's no vertical tangent. If there's no vertical tangent, can that be a cusp? No. To be a cusp, it first has to be a vertical tangent. Let's do the same problem, but pick a different function. So let's say if you have f of x is equal to, okay, we have 10x raised to 2/5. Okay, so let's find the derivative. So we bring the 2/5 in the front, so we'll end up with 20 over 5, which is 4, x raised to negative 3/5. Since it's a negative exponent, let's make it positive. We always want to make our exponents positive. So that is my derivative now. Now we want to check our derivative from both sides. We're coming towards where's x? X is 0. Okay. So we want to take the limit as x approaches 0 from the left, and we want to take the limit as x approaches 0 from the right. So let's do this one. So we have limit as x approaches 0 from the left. We have 4 over x raised to 3/5. And the reason why we are using 0 is because they told us to use that point. This is number over 0. You can clearly see that this is that case. So we pick a number to the left of 0. We're only coming from one side here. So you'll pick negative 0.1. If I plug it in, you take negative 0.1 and raise it to the 3/5 power. That'll give us a negative number still. So we have a negative on the bottom, positive on the top. So this is going to be a negative infinite. Let's do the same thing for this guy, except this time we are coming towards 0 from the right of this function, of my derivative. Remember, we are checking the derivative. If you come from the right, you can pick 0.1. 0.1 raised to 3/5 is going to give us a positive number. So you have 4 divided by 0 is infinite, but because this is positive divided by positive, we're going to get a positive infinite. Because remember, this will give us infinite. It's just a matter of figuring out which infinite. Since these are not the same, that doesn't mean limit does not exist. We're not looking for that. Remember, as soon as one of these derivatives, I should point derivative. Sorry, make sure you guys do that because we're checking the derivative. Okay, so make sure you put primes there. As soon as one of these derivatives is infinite, then we have a vertical tangent. Okay, so I know we have a vertical tangent, and since these infinites are not the same, this vertical tangent happens to be a cusp. So in this example, we have a vertical tangent which happens to be a cusp. Okay. All right, that's pretty much it in that section, but I just want to address a couple more things really quick. Okay. Sometimes we can graph a derivative given a function very easily. So let's say if I give you this function, okay. Okay, so this is 1, 2, 3, this is 1, this is 1, 2, negative 2, okay, and this is negative 2, negative 1, negative 3, okay. So this is the y is equal to f of x. What they want us to do is they want us to graph y prime or the derivative f prime. Okay, so let's do that. Okay, so we're going to graph the derivative. This is x, y prime because we're graphing the derivative. Now remember, the derivative is just the slope of the tangent line. That's what we will always think about that in this class. Okay, all right. So let's see where are the interesting bits here. One of the things we just learned a minute ago is when we have a sharp corner, the function is not differentiable. Do you guys remember that? Okay, so I have 3 points where the function is not differentiable when x is negative 2. So let's plot those points here. We have negative 1, negative 2, we have 1, 2, 3, 4. When x is negative 2, it's not differentiable. So I'll just mark that with a different color for now. Okay. Actually, I'll just underline it. Negative 2, 0. And 2. Because at those places we have sharp corners, so the function is not going to be differentiable there. We're not going to be able to find the derivatives. Now, and then out here, if you notice, this function keeps going here to the left. Out here it stops, okay? If you look at this line here, just this yellow line that I've drawn, if I were to pick a point there and draw a tangent line, won't the tangent line be the same as that yellow line? And if it's going to be the same, the slope of the yellow line and the tangent line are going to be the same. So whatever the slope of the yellow line is, it's going to be the slope of the tangent line. So what's the slope of the yellow line? Well, let's do rise over the run. If you look at this point, what is the rise here? It's -2, and the run is what? -1. Okay. So if you do rise over the run, we end up with the slope is going to be what of that line there, just to the left of -2. The rise is 2 and the run is 1. So we end up with 2, except the line's going down. The slope's going to be negative then because it's going down, you know. Do you guys follow? Okay. So that's how we get that. All right. Or you can also do it this way if you don't see that. This point here is -3, 0. And this point down here is -2, -2. So if you do rise over the run, we get -2 minus 0 divided by -2 minus of -3. So we get -2 over +1, which gives you -2. So from negative infinite to -2, this line will have a slope of -2. And since the tangent line and that line are one and the same, the slope of the tangent line will also be -2. So let's come out here. We have -1, -2. So from infinite to -2, the slope is going to be -2. Okay, so I'm going to draw it. So this is the graph of my tangent line. I'll draw it in blue color. But at -2, because we have a sharp corner, it's not differentiable there. We'll have a hole there. Okay, so you can see to the left of -2, the slope of the tangent of the line of the tangent line is always -2. That means the derivative is always -2, and you can see that. Okay, all right. From -2 to 0, that's this line. Let me use a different color. That's this line. If I pick any point on that line and draw a tangent line, it's going to be exactly the same as that yellow line. So the slope of the tangent line is going to be the same as the yellow line. So what is the slope of the yellow line? Well, you can do rise over the run again. The rise is what? -2 and 1. So the rise is 3. And the run is what? From -2 to 0 is 2. So it'll be 3/2. And since the line's going up, it's going to be positive. So out here, it's 1.5. So you go up here, there's a hole. There's a hole here at -2 again because of this sharp corner. It's not differentiable there. And then we go up to here. That's 1.5. 3/2 is 1.5. Now what happens? If I go from 0 to 2, I get this line. If I draw a tangent line here, it'll be the same as the pink line. So the slope is going to be the same as the slope of the pink line, which is 0. So from 0 to 2, the slope of the tangent line is always 0. So you come down here, there'll be a hole here, by the way. Why will there be a hole? Because we have another sharp corner here, you know, so it's not differentiable there. But then it's 0 all the way up to 2, and there's a hole there. You can see the slope of the tangent line between 0 and 2 is 0 because the line is horizontal. And then the line goes down here. So let's use, I'll use a different color here. Okay, pink. So the slope's going to be negative. If I draw a tangent line, it's going to have the same, it's going to look the same. So what is the slope? Rise over the run. The rise is 1, the run is 1, except the line's going down. So the slope there is what? -1 since it's going down. At 2, we have a sharp corner, so we have a hole there, and then it's going to be -1, so we'll have a hole down here, up to 3, and we'll have a hole here. And the reason we have a hole here is because we can't come from this side to take the limit at all, so we can't differentiate here. Is that okay? I mean, you can find one-sided limit if you wanted to, but for now, I'll just put a hole there. Okay? So this is the graph of the derivative, and we did this without actually finding the function y prime. They didn't even give us this function, they just gave us a graph of that function. So always remember the derivative is just the slope of the tangent line. So on this graph, we're just graphing the slopes of tangent lines starting from left and going this way. Okay? All right, I think that's about it in that section. There might be a thing or two that I didn't get done, but I will mention that in class. So hopefully that'll tie up all the loose ends. Okay?